Welcome back to Statistics Made Simple, and I am Savita Balsang. This video is based on finding solutions to problems on the chi-square test for goodness of fit part 3. And these problems are 10 markers and very important from the examination point of view. This video focuses on the third type of problems on chi-square test for goodness of fit. Here, we have to fit either the binomial distribution or the Poisson distribution for the given data and then test whether the distribution is a good fit to the given data. Like I already mentioned, these problems are important 10 markers. Problem 7. 5 identical coins are tossed 128 times. Their results are tabulated below. First subdivision, assuming the coins to be unbiased, fit a binomial distribution and test whether the distribution is a good fit. Second subdivision, estimate from the data the parameter of the binomial distribution and fit a binomial distribution and test for goodness of fit. Here, subdivision A and subdivision B are for 10 marks each. In the first column, we have number of heads given 0, 1, 2, 3, 4, 5. In the second column, the number of tosses are given as 25, 40, 43, 15, 4 and 1. Now note that the given frequencies are also called as the observed frequencies. So the first column, that is number of heads, is denoted by small x, and the last value in the x column is 5, which is nothing but small n. The number of tosses is marked as f or o. That is the frequencies or the observed frequencies, and when we add up these frequencies we get capital N equal to 128. This problem is an important one. Do practice and understand the concepts thoroughly. Starting with the solution for the first subdivision, write given small n is equal to 5. Then capital N is equal to 128. Now because of the word unbiased in the problem, the probability of getting a head is 0.5. So P is equal to 0.5 or half, and within brackets you can write the reason because the coins are unbiased. Then find out Q, which is 1 minus P, which is 1 minus 0.5, which is equal to 0.5. And since alpha is not mentioned in the question, you take it as 5%. The next step is to first fit the binomial distribution to the given data under the condition that the coins are unbiased. So define capital X as number of heads. So the PMF of the binomial distribution is given by P of x equal to, open the flower bracket, NCX P to the power x Q to the power n minus x, where x takes the value 0, 1, 2, so on till n, and Q is equal to 1 minus P, 0 otherwise. Now in the next step, for n, substitute the value 5, for P 0.5 and Q is also 0.5. So you get P of x equal to, open the flower bracket, 5C x 0.5 to the power x 0.5 to the power 5 minus x, where x takes the value 0, 1, 2, 3, 4, 5, 0 otherwise. Here, now I am going to substitute different values for x and find out the corresponding probabilities. So when x is equal to 0, P of 0 is 5C 0, 0.5 to the power 0, 0.5 to the power 5 minus 0, which is equal to 1 into 0.0313, which is equal to 0.0313. Similarly, put x equal to 1 in the PMF. So you'll get P of 1 is 5C1, 0.5 to the power 1, 0.5 to the power 5 minus 1, which is equal to 5 into 0.5 into 0.0625, which simplifies to 0.1563. Similarly, when x is equal to 2, P of 2 is 5C2, 0.5 to the power 2, 0.5 to the power 5 minus 2, which is equal to 10 into 0.25 into 0.125, which is equal to 0.3125. When x is 3, we get P of 3 is 5C3, 0.5 to the power 3, 0.5 to the power 5 minus 3, which is equal to 10 into 0.125 into 0.25, which is equal to 0.3125. When x is equal to 4, I get P of 4 is equal to 5C4, 0.5 to the power 4, 0.5 to the power 5 minus 4, which is equal to 5 into 0.0625 into 0.5, which is equal to 0.1563. When x is equal to 5, P of 5 is 5C5, 0.5 to the power 5, 0.5 to the power 5 minus 5, which is 1 into 0.0313, and you know that 0.5 to the power 0 is 1, which is equal to 0.0313. Now observe that the probabilities are symmetric. We know the property that for the binomial distribution, when p is equal to 0.5, the distribution is symmetric. So we observe that the values of the probabilities at the beginning and at the end are the same. Note that in the previous slide, I found out all the probabilities by substituting the x values in the PMF. If needed, you can find out first P of 0 and then find out the remaining probabilities using the recurrence relation between successive probabilities, or you can also use the recurrence relation between successive frequencies and find out the expected frequencies in a different way, like I have done in my video on fitting of a binomial distribution. Please adopt whichever method is easy for you. Now I will rewrite the table where in the first column I have number of heads as x and the values are 0, 1, 2, 3, 4, 5, and you know that the last value in the x column you mark it as n. Then the number of tosses are the frequencies or the observed frequencies O. So the values are 25, 40, 43, 15, 4 and 1. And when we add up these values, we get capital N equal to 128. In the third column, form P of x, which are the probabilities we just now calculated, that is 0.0313, 0.1563, 0.3125, 0.3125, 0.1563 and 0.0313. Now, the most important step is to find out the theoretical frequencies or the expected frequencies, which are denoted by Tx and which has a formula capital N into P of x. So 128 into 0.0313 gives us 4.0064, which you can approximate as 4. Then the next value is 20.0064, you approximate it to 20. So take each probability and multiply with 128 to get the theoretical frequency. So the next value is 40. Then again we have 40, 20.0064, which you approximate to 20, 4.0064, which is equal to 4. So when we add the theoretical frequencies 4, 20, 40, 40, 20 and 4, which are highlighted in black color, it gives us the total as 128. So the sum of the theoretical frequencies and the sum of the observed frequencies should match and both are equal to 128. Note that the theoretical frequency Tx is also called as the expected frequency, which is denoted by E when we do chi-square test for goodness of fit. So till here, if we fit the binomial distribution correctly and find out the expected frequencies, it carries 5 marks. Now the remaining 5 marks is testing whether the binomial distribution is a good fit to the given data or not. Let us now test whether the binomial distribution is a good fit to the given data. So first write H0. Binomial distribution is a good fit to the given data versus H1. Binomial distribution is not a good fit to the given data. Now let me first form a table which is on the extreme left of the slide. So in the first column, I have the observed frequencies or the frequencies which were given to us in the problem, that is 25, 40, 43, 15, 4 and 1. So summation O is equal to 128. In the second column, write down the expected frequencies or the theoretical frequencies which we found out, that is 4, 20, 40, 40, 24, and you get summation E equal to 128. Now remember that whenever we make use of chi-square test for goodness of fit, all the expected frequencies should be greater than or equal to 5. Now you will observe that the first and the last expected frequencies are 4, which I have highlighted in red color, and these two values are less than 5. So we have to adopt what is called as the method of pooling. So when we pool the value of the expected frequency which is less than 5, either with a value which is preceding it or succeeding it, correspondingly we have to also pool the observed frequencies. Otherwise what will happen is the number of observed frequencies and the number of expected frequencies will not match in the two columns. So let me write the statement that since the first and the last expected frequencies are less than 5, we use the method of pooling. So this statement is important to write. Now look at the second column which has the expected frequency. So 4, it is less than 5. So this 4, it has to be added to the value which is succeeding it, that is 20. So you have to add 4 and 20 and you will get 24, and 24 is a value which is greater than 5. Okay, similarly if you take the last two values, the last two values are 4 and 20. So when I add this 4 and 20, I will get 24. So the corresponding observed frequencies also should be added. So when I add 25 and 40, I will get 65, and when I add 4 and 1, I will get 5. So remember that it is important that the expected frequency should be greater than or equal to 5. But if the observed frequencies are less than 5, it does not matter. But whatever expected frequencies we are pooling together, the corresponding observed frequencies also should be pooled, because the number of values in both the columns will not match otherwise. So let us again rewrite the table. So I'll get the observed frequencies after pooling as 65, 43, 15 and 5, and the expected frequencies after pooling are 24, 40, 40 and 24. Then find out O minus E the whole square. So I'll get 1681, then 9, 625, 361. Then calculate O minus E whole square by E, which is 70.0417, 0.225, 15.625, 15.0417. So summation O minus E whole square by E is equal to 100.9334. This requires a bit of practice, so understand the concept thoroughly and practice all the steps. Under H0, the test statistic is chi-square equal to summation O minus E whole square by E, which follows chi-square n minus 1. The condition which we use for chi-square test for goodness of fit is you have to check if chi-square is greater than K2, then you will reject H0, otherwise you will accept H0. So you get chi-square from the table as 100.9334. So for testing of hypothesis, n is equal to 6. which stands for the number of independent variates. Okay, this is a very important point to remember. Initially, when we fit the binomial distribution, n is the last value in the x column. So when we fitted the binomial distribution, we took n as 5 because for the binomial distribution, the range is 0, 1, 2, so on till n. N was taken as 5. But in testing of hypothesis, in the degrees of freedom, n stands for the number of independent variates, and so n is equal to 6. So the degrees of freedom is n minus 1, and because we have pooled twice, that is once at the beginning and once at the end, it means we have pooled twice, so we have to reduce 2 degrees of freedom. So you get 6 minus 1 minus 2, which is equal to 3. So at 5% level of significance for 3 degrees of freedom, K2 value is 7.81. Conclusion. So since chi-square is 100.9334 is greater than K2 equal to 7.81, at 5% level of significance for 3 degrees of freedom, we reject H0 and conclude that the binomial distribution is not a good fit to the given data. With the second subdivision, let us first fit a binomial distribution to the given data, and in the second subdivision the value of p is not given and we have to estimate the value of p. So write given small n is equal to 6, capital N is 128 and alpha is 5%. X denotes number of heads. Then form the given table. The first column number of heads, mark it as X. The values are 0, 1, 2, 3, 4, 5. And the last value in the X column, you should mark it as small n. Then the second column has number of tosses, which is denoted by F or O, and the values are 25, 40, 43, 15, 4 and 1. And you get capital N equal to 128. Now, since the parameter p is not known to us, we first need to find out the mean of the given problem. So for that, we need to form the fx column and we get the values as 0, 40, 86, 45, 16 and 5, which gives summation fx is equal to 192. Let us now find out the mean for the given problem, that is x bar is equal to summation fx by capital N, which is 192 divided by 128, which gives x bar equal to 1.5. Obtain the value of the parameter of the binomial distribution, we use the property, that is, we know that the mean of the binomial distribution has to be equated to the mean of the binomial distribution, which is NP. So we know that x bar is equal to NP, which implies P is equal to x bar by N, which is equal to 1.5 by 5. So you get P equal to 0.3. And q is equal to 1 minus p, which is 1 minus 0.3. So you get q is equal to 0.7. Let us now find out the PMF of the binomial distribution. So first, writing the general format, we get p of x equal to, open the flower bracket, ncx p to the power x q to the power n minus x, where x takes the values 0, 1, 2, so on till n, and q is equal to 1 minus p, 0 otherwise. Now in this PMF, substitute n as 5, p as 0.3 and q as 0.7. So you get p of x equal to, open the flower bracket, 5cx 0.3 to the power x 0.7 to the power 5 minus x. X takes the value 0, 1, 2, 3, so on till 5, and you get 0 otherwise. Problem, I am obtaining the probabilities by substituting different values of x in the PMF, and like I have already mentioned, you can make use of the recurrence relation between successive probabilities or successive frequencies and then get the probabilities and the theoretical frequencies. So when x is equal to 0, p of 0 is 5c 0, 0.3 to the power 0, 0.7 to the power 5 minus 0. which is equal to 1 into 1 into 0.1681, which is equal to 0.1681. When x is equal to 1, we get P of 1 is equal to 5C1, 0.3 to the power 1, 0.7 to the power 5 minus 1, which is equal to 5 into 0.3 into 0.2401, which is equal to 0.3602. When x is equal to 2, we get P of 2 is equal to 5C2, 0.3 to the power 2, 0.7 to the power 5 minus 2, which is equal to 10 into 0.09 into 0.343, which is equal to 0.3087. When x is equal to 3, P of 3 is equal to 5C3, 0.3 to the power 3, 0.7 to the power 5 minus 3, which is 10 into 0.027 into 0.49, which is equal to 0.1323. When x is 4, P of 4 is 5C4, 0.3 to the power 4, 0.7 to the power 5 minus 4, which is equal to 5 into 0.0081 into 0.7, which is equal to 0.0284. When x is equal to 5, P of 5 is 5C5, 0.3 to the power 5, 0.7 to the power 5 minus 5, which is equal to 1 into 0.0024 into 1, which is equal to 0.0024. Let us now form a table where we will write down the number of hits and number of tosses which is given in the problem. Then also form the columns P of x and Tx equal to capital N into P of x. Number of hits is marked as x and the values are 0, 1, 2, 3, 4, 5, and the last value in the x column is marked as small n. The number of tosses are f or the observed frequency is O, and the values are 25, 40, 43, 15, 4 and 1, which gives capital N as 128. Then write down the corresponding probabilities P of x, which is 0.1681, 0.3602, 0.3087, 0.1323, 0.0284 and 0.0024. The next step is to find out the theoretical frequencies Tx, which is equal to capital N into P of x. So the first Tx value will be 128 into 0.1681, which gives 21.5168, which is highlighted by a pink asterisk, and after approximation it is 22. The next value we get is 46.1056, which is approximated to 46, 39.5136, which is highlighted with a pink asterisk, is approximated to 40. Similarly, 16.9344 is approximated to 17, 3.6352 is approximated to 4, 0.3072 is approximated to 0. I am sure all of you are aware, if the value after the decimal is equal to 5 or greater than 5, then the previous digit will get increased by 1. That's what we have done here. So when we add up the theoretical frequencies 22, 46, 40, 17, 4 and 0, we get the total frequency as 129, whereas the total frequency should be equal to 128. Okay, so what we have to do is we have to adjust one of the frequencies so that the sum is equal to 128. Now for the values which are marked with the pink asterisk after the decimal, you see that the value after the decimal is 5. So here 21.5168 can be taken as 21 instead of 22, or the other value, that is 39.5136, can be taken as 39 instead of 40. So what I am doing here is, here I am taking 21.5168 as 21 and proceeding. So the final expected frequencies are in the fourth column, and the final Tx value using this approximation is 21, 46, 40, 17, 4 and 0, which gives a total as 128. Now, another important point to remember is depending on which value is adjusted or approximated, the chi-square value will change, but the conclusion as to whether you are accepting H0 or rejecting H0 will remain the same. Fitting of the binomial distribution is complete and we have got the expected frequencies. The next step is to test whether binomial distribution is a good fit to the given data or not. So write H0 as binomial distribution is a good fit to the given data versus H1 binomial distribution is not a good fit to the given data. Then form a table with two columns, that is the observed frequencies which is given to us in the problem and the expected frequencies or the theoretical frequencies which we just now calculated. So the observed frequencies O are 25, 40, 43, 15, 4 and 1, and we get summation O equal to 128. The corresponding expected frequencies are 21, 46, 40, 17, 4 and 0, and summation E is equal to 128. Now observe that the last two expected frequencies, that is 0 and 4, are less than 5. So we have to make use of the method of pooling. So first let us add 0 and 4, which are highlighted in red color. So when we add 0 and 4, we get the total as 4. Now 4 is again a value which is less than 5. So 4 should be added to 17 and we get the corresponding expected frequency as 21, which is a value greater than 5. Whatever we have done with the expected frequencies, the same procedure should be adopted for the observed frequencies which have highlighted in the blue color arrows. So add 1 and 4 and you get 5. 5 plus 15 is 20. Now keep in mind that it's not important that the observed frequency should be greater than or equal to 5. They can be even less than 5. But the expected frequency should always be greater than or equal to 5. And whatever adjustment or pooling we do for the expected frequencies, same has to be done for the observed frequencies. Otherwise, the number of values in both the columns will not match. Now form another table where the observed frequencies are written after pooling, that is 25, 40, 43 and 20. Similarly, the expected frequencies after pooling are 21, 46, 40, 21. Then find out O minus E whole square, which is 16, 36, 9 and 1. Then O minus E whole square by E is 0.7619, 0.7826, 0.225, 0.0476, which gives summation O minus E whole square by E as 1.8171. Write the test statistic formula. Under H0, the test statistic is chi-square equal to summation O minus E the whole square by E, which follows chi-square n minus 1. So from the table, we get chi-square equal to 1.8171. The condition for goodness of fit test is you have to check if chi-square is greater than K2. If it is greater than K2, reject H0, otherwise accept H0. Now for testing of hypothesis, the total number of independent variates is n equal to 6. The degrees of freedom is n minus 1, and because we have pooled twice, you have to subtract 2, and we have estimated the parameter p, so we reduce 1 degree of freedom. So keep in mind that the degrees of freedom is only n minus 1, but whenever we pool, we have to reduce that many degrees of freedom. When a parameter is estimated, we reduce 1 degree of freedom. So we get the degrees of freedom as 6 minus 1 minus 2 minus 1 equal to 2. And at 5% level of significance for 2 degrees of freedom, K2 is 5.98. The conclusion, since chi-square is 1.8171, is not greater than K2 equal to 5.98, at 5% level of significance for 2 degrees of freedom, we accept H0 and conclude that the binomial distribution is a good fit to the given data. Fitting of the binomial distribution and then checking for goodness of fit is an important 10 marker. So please understand the concepts well and practice all the problems. Thank you all for watching and look out for my next video where I'll fit a Poisson distribution and then check for goodness of fit, which is again a 10 marker.